So before maybe I start sharing my slides, I can just give a little background on myself and context. So my background is also on computer science. I have a PhD in computer science, but I've always been interested in space. So recently, last December, I finished my master's in astrophysics. And I'm currently doing an internship in AI and machine learning at the European Space Agency Operations Center in Germany. And today the talk is about astrophysics and galaxies, but I think this is much in line with the topics you mentioned, because there's a lot of things going on right now related to these topics in operations, because there's a lot of data coming in from space instruments, and there's a huge opportunity to come up with these smarter ways to process this data, either on spacecrafts, on board processing, or even on the ground. So everything we will talk today, I think it's relevant, and there are many opportunities to transfer these topics to real problems today in the field of space operations and mission design and things like that.
Yes, indeed. And also what I can add is in the field of in the area of space, I think what we could see as one of the most applied or mature area of AI is probably Earth observation or usage of satellite imagery in visible or in other spectral domain. I think this exploded a lot and it's very popular. And now it starts to also reach other domains like the one you will talk about, but also operations. So it's great, yeah. Okay.
So I think you can see my slides, okay?
Yes, very well, thanks.
Okay, so this presentation is the work that I did for my master's in astrophysics. And again, we are bringing these two areas of interest together, space and artificial intelligence. And in a nutshell, what this work is about is trying to do this galaxies characterization, coming up with these properties of interest about galaxies, while exploring machine learning approaches. These are the two fields that we are trying to bring together. And in a nutshell, we do this by creating models, composing them into pipelines. And this, I will come back to this later, but this is very relevant for space operations today. And because we want to be able to apply these models and all these pipelines in a systematic way to flows of data that are coming in from spacecrafts to the ground. And why do we do this, or why this is relevant in the specific field of galaxies? Because galaxies are a fundamental object when we talk about space science and when we talk about the universe and the evolution of the universe. And also galaxies provide us, from a physics standpoint, a very interesting way to study some physical phenomena. So I wasn't sure on the background of the people that were going to join the discussion. So I included a couple of slides from the astrophysics side of things and from the deep learning side of things. And I will try just very briefly and very simply go over these things, so at least we are at the same level for discussion. So first thing is galaxies. What are galaxies? Usually we define galaxies as this collection of objects that are gravitationally bound together. They stick together due to the effect of gravity. And as is often the case when we are talking about astrophysics, we can't study these objects in a laboratory on Earth. You can't pick up a galaxy and put it on a scale to know how much it weighs or measure its length with a ruler. So we rely on indirect methods to do these studies. We get our observations from instruments on the ground or in space, and we try to do these indirect measurements. And again, galaxies are the building blocks when we are describing the evolution of the universe. Just to illustrate this, I have here a little simulation that I hope it's working and you are seeing. Yep. This is an example of an evolution of the universe where we start with a blob of gas that will eventually, with gravity and other phenomena, will come together to form the structure that we see in the universe today. And we are seeing here is that the orange part of the simulation represents gas, and the purple part represents dark matter. And we see how this gas comes together with help of the dark matter to form the galaxies that we see today, and the stars and everything else. Another thing that's very interesting about galaxies, and it provides very useful information, it's morphological classification, how galaxies look like. When you look at a galaxy just by a visual inspection, is it more blue, more red? Is it more elliptical or spiral? All this gives us information about the contents of the galaxy and how it evolves. And this relates with actual physical properties. Here we have an illustration of very beautiful image took by the Hubble telescope. And we can see there's a huge variety of galaxies just by a visual inspection. Another thing that provides us lots of information is this broad field of spectral analysis. Spectral analysis, it's about studying the electromagnetic radiation and how it interacts with matter. This gives us information about which elements are present not only in galaxies, but in what lies between us as the observers and the galaxies that are far away. Just to illustrate this phenomena, we have here a light source that we put through a prism, and then we can see all the wavelengths, the different wavelengths, the continuum of the light. This is the effect that you get, for example, when you look at the rainbow. But if you can look in more detail at this light continuum, for example, when the light comes to us from the sun and traverses the atmosphere, some part of this light in some specific wavelengths will interact with the elements in the atmosphere. And we can see this in the spectrum that gets to Earth. There's this called absorption lines, that they are an exact signature of the element that the light crosses before getting to us. And this gives us lots of information about the elements that are between us and the sun. And of course, if you just look at the gas, it will also emit its own signature. We can see that in the light spectra. And if we take a look at a more closed and more detailed information about this spectra, usually what we see is this plot of the flux that we get over the wavelengths. And this can also be useful to extract other information, like, for example, the redshift. So as I said, when light passes over a gas, you get a very distinct signature because different elements will absorb different wavelengths. And you can study this in laboratory here on Earth. So for example, you make light cross only hydrogen, and you can see in the spectra which wavelength was absorbed. And when we look at the spectra from a galaxy, we can try to see where this feature is in the spectra. Here, for example, in this example, we are looking at the hydrogen emission line, and we can see there's a difference between the wavelengths that we get from the laboratory on Earth and the actual wavelengths that came from a distant galaxy. And this is due to the fact of the cosmological expansion of the universe. As the light is traveling through the universe between a distant galaxy and us, the observers, its wavelength gets shifted to the red, just because the space-time that the light is traveling to is expanding, and the wavelength is getting shifted to the red. This is, for example, if you look at the James Webb Telescope, the optimal wavelength that they tried to do for the telescope observation was in the near infrared. And this was because they wanted to observe objects that are really, really, really far. And so the wavelengths get stretched to the near infrared. And this, you can extract lots of information from this spectra. The cosmological redshift gives us an idea of how far the objects are. Because as much as the line is shifted, it means that it traveled more time in this expanding universe before arriving at our detector.
That's a good explanation. I mean, can we make an analogy with sound, maybe? So, do you know if it makes sense to say it's analogous to when there is an object on Earth, like a truck emitting a sound that goes away from us and comes, like the Doppler effect? Is it something?
Exactly. It's another way of looking at the Doppler effect. But okay, the reasoning is exactly the same. As an object is coming towards you or going away from you, it will compact or extend the wave sounds that you get. And that's why you see that effect of an object coming towards you or away from you. It's the same reasoning. It's just another way of looking at the same effect.
Okay, so I already see like two tricky things. The first one being that yes, we cannot put galaxies in a bucket and study them in the lab, and also we have this challenge of the redshift values, because when we do the experiment in a lab, we expect it to not be shifted, but the light that comes from the galaxy is actually shifted. So this adds again a challenge, right?
Yes, this you can think of this as every kind of this detail will add a new challenge or difficulty to analyzing this kind of spectra. And there's a lot of corrections that you need to do to these things to see these, let's say, pretty plots, because this is not so easy to measure as simple as we are discussing here. Especially, for example, if you are observing from the ground, you have the turbulence from the atmosphere, and the atmosphere is opaque in some wavelengths. So you have to consider all those corrections in your instruments, or better, when you use the data from those instruments, you have to figure out all those corrections. So again, the spectra gives also information which kind of galaxy we are looking at, because we classify galaxies in different ways. We can have, for example, starbursts, which are galaxies that are going through an intense star formation rate. We can have galaxies that have an active supermassive black hole in the middle. But just from some visual inspection of the different spectra that we see here, we can see that these are fundamentally different. So there's a lot of information we can try to pull from this spectra data. Of course, all this is very interesting, but we want to look at this information in large volumes, because usually, or many studies in galaxies are based on statistical analysis. You say this group of galaxies shares this kind of feature, so probably they went through the same evolution process, or they have some characteristic that it's common. And so the interesting thing is that there are a lot of surveys, they are called usually surveys, of these galaxies, where you can find this information for a lot of objects. Because this spectra will, even if we are talking about the same type of galaxies with the same characteristics, this morphological classification and this spectra, this will change slightly. So we need to look at many objects. And fortunately, we have these surveys, like, for example, the Sloan Digital Sky Survey, that provides us with this information from millions of objects. And the Wide Field Infrared Survey Explorer is another mission where we have more information about galaxies, and these observations are usually done at different bands, what's called bands, different parts of the spectra. So the idea is be able to combine these things together, because the more things you can combine together, the more sources of information, you will be in a better position to come out with interesting results. And besides these observation surveys, there are also very interesting projects, like, for example, the Galaxies project, which is a crowdsourcing project. And this was done by volunteers. And anyone could register and participate. And what they did was very interesting, because they shown people's images from galaxies, and then you will answer some kind of questions about just visually inspecting the image. So is the galaxy like a spiral? It has a bulge in the middle. And lots of people came together to do this, and then they did a statistical analysis on top of the answers, and they built this very interesting classification tree for galaxies. And this today is still a very valuable source of information, because we are talking about a lot of people contributing and a lot of galaxies that were analyzed. So this ends a little bit my slides about the astrophysics side of things. I see that many people are from the AI part and communication from CS. So I'll just go briefly over these slides that I had more about deep learning. So in this specific case, we are, if you want to look at these fundamental relations between these topics, we are working at the machine learning level. We are trying to come up with mappings between the data that we have and the features or the characteristics of interest that you want to look at. And in specific, we are in the field of deep learning because we are building deep neural networks. And if you want to take a look at the branches that usually people discuss about in machine learning, we are in the branch of supervised learning. Because we have the data inputs, and we also have the outputs for the characteristics of interest that we are interested in analyzing. And the idea then is to come up with these artificial neural networks. And so we have an artificial neural network is, in a nutshell, illustrated in this figure, where you have the input layer, which in our case, it will be well defined because we have the data and we have we know the information we want to look at. And we also have the output layers very well defined. So the challenge is to come up with this hidden layer part, what usually we call the architecture of the network, because this architecture of the network will enable us to build a mapping between the inputs and the outputs. And this is very challenging, as we all know, because it can't be too simple, this network in the middle, because otherwise you may not be able to capture the mapping between the input and the output. But at the same time, it can't be too complex, because if it's too complex, probably you don't have the data at enough level of precision to come up with an interesting mapping. So the first challenge is to come up with these architectures in between our inputs and outputs. And just very quickly, after we have the architectures defined for our network, we will want to train it. And again, we are in the branch of supervised learning, so we have inputs and outputs. And the training goes in a nutshell in 4 major steps. First, you do a forward propagation of the network, where you apply your network that was probably randomly initialized. And you apply that network to your inputs, the outputs come out on the other side. You compare that with the actual outputs that sometimes we call the ground truth that we have. We measure the difference between the outputs that we have and the outputs that are the ground truth. We propagate that on the new step back through the network. And then there's some kind of optimizer that will update all the weights in your network. And then you iterate over this loop until you come up, hopefully, with an interesting mapping that is able to predict the outputs from the inputs. So, put it very simply, after the architecture and the inputs and the outputs defined, we basically need to come up with an optimizer and a loss function. And of course, there are lots of there are lots of other parameters that you need to define for your network, which activation functions to use, what's your learning rate and batch size, and the number of epochs that you are going to train. And all of these need to be chosen up to some level. You have some options to choose from this, but all of these will have an impact on the ability of your final models to correctly or not correctly infer your outputs of interest. So this was my quick background over the astrophysics side of things and the deep learning side of things. And then I will start discussing in more detail what we did for this specific example. So we divided this work in 3 major parts. And the first part is about data. So we are in supervised learning branch. We need to come up with inputs and outputs for our model. And the way we approached this was starting with the SDSS survey. The SDSS survey is very interesting, and it has a lot of data. I mean, really a lot. And some data is not so much suitable to use in practice. So what we did was create a subset of this data. So we selected 100,000 random objects from the survey that were classified as galaxies. These were stratified on subclass. This means that in our subset, we have roughly the same distribution of subclasses that the original dataset. I will come back to this detail in a bit. And for each object, we organized all the information that we need, because in the databases from the dataset, you get this information from different places and different catalogs, but we organized everything together very nicely. And then we also included for each object a RGB image and the fits and spectral data. The data fits, it's a format for sharing scientific data, where you can share basically n-dimension arrays of data. But if you want to think about it, fits was the data that came out from the CCD that took the image. So they pointed the telescope at some patch in the sky and they took an image of it. And the fits carries that information that was recorded by the CCD.
So is it kind of a raw image or a raw tensor of values?
It's not raw because it's processed. It has some corrections on it, like, for example, the atmospheric corrections and other things, but is, let's say, as much raw as you can get. All the other data that it's in the data set has more processing on top of it. When you look at the fits data, you're as close as possible to the raw data. And just to give an example, here's a random object from the data set. You can see the RGB image here for that object. And if you compare these to the image that we saw from the Hubble telescope, you see that these are fundamentally different. The level of quality is, of course, very, very different, but you couldn't do this kind of surveys using the Hubble telescope, because to get those images, you need hours of exposure and lots of things going on. And to do millions of objects using Hubble will just not be possible. And here you can see the fits data, the different bands that, because let's call it CCD, is taking a snapshot in these 5 different bands. And you can also see the spectra here. We also did another option here, because we are storing the full spectra. This means that for the entire wavelengths that the instrument that was used is able to record. But we are also storing what we call these selected bands of the spectra. In this case, we don't store the entire spectra, the entire wavelengths the instrument is able of capturing. We just store these specific wavelengths. And we will see why in a little bit. And on top of that, you still have the bands information. These bands information these come from the photometric analysis of the object, where they look specifically at the object, do a lot of corrections, they correct for the distance of the object, and they give you this very precise, up to some point, levels of the flux, the measure of the energy that was received over these bands. And here we see the bands that come from the SDSCS and the bands that come from the WISE survey. And we can see that these are different values because these are from different bands and a lot of different characteristics here. And we can also see that the properties, we did this very quick exploratory analysis on the other features of interest, like the redshift. We can see that for the random objects that we selected, we have much more objects closer to us. And the same with the stellar mass. We have much more galaxies that are, let's say, smaller when we are talking about galaxy size than galaxies that are big. And here we see the distribution of the subclass of the galaxies. They classify these as star-forming, starburst, broadline, or AGN. And we can see that most of the galaxies are classified as star-forming. And finally, we can see the distribution of values for the galaxy zoo classification. And here, the most common object are spirals. So this was the data part. So now we have this data set with all the information, the data that we want, very well organized. So we started to create models to use this data. Just to define our models in a more kind of formal way, a model for us in this case is something, a function, a mapping, or whatever you want to call it, that takes a collection, a list of inputs and produces a list of outputs. These are our modules. And we will see later why we feel that this kind of description of things is relevant. So we started to define very well what are our inputs and outputs for our models. In our inputs, we can see that we have the image and the fits data, which are n-dimension tensors, if you want to call them like that. We have the spectra and the selected bands, which are arrays. And then we have the bands and wise photometric values for each specific band, which are also arrays. And as outputs, we are interested in calculating the redshift, the subclass, the stellar mass, and the galaxy zoo classification. So we have two variables of interest that we see as a regression problem. The redshift and stellar mass are real numbers, and the subclass and the galaxy zoo classification are classification problems. We want our model to output a class. So from my earlier figure, we have the inputs and outputs well defined. So the next step was actually to start defining these architectures for our networks. So the first step, and it seems the more immediate one, is to build one network that takes one of each input and produces and tries to infer the redshift. So we created one model for each input and output the redshift. And this each box in this diagram represents a hidden layer in our networks. And for the fits and image, we use a convolution layer with a ReLU activation. And for the spectra, we also use the convolution layer, because although we are talking about only one dimension, it's an array of numbers. As we have seen, the features of interest in the spectra may shift a little bit to the left or to the right. And usually a convolution layer is very, very good at being translation invariant, which means that we'll try to pick up the feature even if it changes in its position in the array. And for these last ones, we also include a normalization layer, and the output layer is just a ReLU activation function because we are trying to come up with a real, we are trying to predict a real number. So these were the first 6 models that we created. Next, we also wanted to look at stellar mass. So we created another 6 models, one model for each input that we have and outputs the stellar mass. And the reasoning follows more or less the same for the model's architecture. And then we created another 6 models to compute to try to infer the subclass, 1 from each input. And the difference here is mainly at the output layer, where we use activation function as a softmax to give us a class. You will notice that these models are not exactly the same. They have different layers because after all the models were trained to some level, we did some fine tuning of the architecture of the model because of overfitting and other phenomena. So these are slightly different.
So sorry. So
Sure.
what you mean is that these individual models for each inputs, they have been partially hyperparameter optimized.
Yes.
Okay.
I will come back to that in a couple of slides.
Great. Okay, cool.
So we also created another 6 models, 1 from each input, to try to do the classification. You see, for example, here, this model, I don't know if you can see my mouse.
Yes, I think, yeah, I see it.
Okay, so yeah. The model that tries to output the galaxy classification, the Galaxy zoo classification from the spectra, it's actually much more complex because we will see that this was the model that was more challenging. And even this more complex model wasn't able to capture the mapping that we wanted. But then we started thinking, okay, but maybe if we put all the inputs together and try to output, for example, the redshift, our mapping will be able to look at more information. And this is a little bit going towards this machine learning paradigm where you don't want to tell the machine the rules. You want the machine to come up with the rules by itself. So we just created a model. We give all the inputs to this model and try to compute to infer the redshift. And we did another one for the stellar mass, and another one for the subclass, and another one for the Galaxy zoo class. But then we also started thinking, okay, but what about the relations between the outputs? Because even if we are trying to infer the redshift or the stellar mass, there is a lot of fundamental physics there that it's the same. So even if a machine comes up with a mapping that is able to infer the redshift, the same mapping needs to, up to some level, be able to go and infer the stellar mass, because E equals mc squared in either case. And there's a lot of physical constraints and knowledge that is common to those things. So we created these models where we give them some of the inputs only, and one model to come up with the regression variables that we are interested in, the stellar mass and the redshift, and another model that we give some of the inputs and tries to come up with the classification for the subclass and the Galaxy zoo. And finally, we took this a little further. Okay, if the model is able to explain the redshift and the stellar mass, so it needs to be able to classify the galaxy, because there's a lot of common fundamental knowledge that these things need to be able to explain at the same time. So we created a model that gets all the inputs, comes up with this latent space representation for the information that the model, after the training loop, thinks it's suitable, and then it has a couple of fully connected layers and outputs all the variables of interest. And so we came up with all these architectures. In total, if I'm not mistaken, these were 31 models. And then we get to the part that you, Patrick, were talking about. Now we need to train these things, and to train these models, we need to define hyperparameters, and we need to define the loss functions and the gradients and so on. So in this part, we did a little bit of brute force exploration. What we did is, okay, let's get each one of these models. We only did this for the single input, single output models because of time, but the same reasoning would apply to all the others. So let's try all these models with different combinations of batch sizes and different optimizers, and look at all the scores that came out of this training process. We did this with a smaller data set. We didn't use the entire data set for these experiences. So we did this for all the models, and then look at all the scores, and then use this to guide our selection of the optimizers and the batch size and the other hyperparameters. So I don't want to go into the details, but in a gist, that's the idea. And then after having all these selected, we finally got to the training loop for it. So what we are seeing here are the plots for the training. And during the training, we split a little bit of the data set for testing. And that part of data set is never seen by the models during the training. But we also split a little bit of the data set to do this validation analysis throughout the training process. And what we see in these plots in blue is the training data set loss, and in orange, the validation data set. And besides the different scales of the plots, we see that there are weird things going on here. For example, in these models, we can also see a little bit of overfitting. But in this, for example, plot in the top right, something weird is going on, because the model started to learn, but then it started to unlearn, or something went on. And this we didn't look at yet at too much details to all of these cases because of time, but there's something interesting things going on here. And this was for the regression problems. And here we see the plots for the classification problems. Again, we can see that there are some cases with a little bit of overfitting. Maybe the model needs some dropout layers or something like that. But in general, we see that the models are learning. The curves for the validation accuracy follow that typical trend that we are used to see, but there's still a lot of work to do in this part. We can definitely improve these results. But nevertheless, the results that we get are already very interesting. And here we see the final results of applying the models to the test set. So the test set is never seen by the models during training. And we can see, for example, for the redshift, to predict the redshift, the model that performs better is the one that has the spectra as an input, which it makes sense, because as we were discussing earlier, we calculate the redshift from the spectra, so it makes sense that all the information is there. And the same for the stellar mass. We see that the best result actually is very interesting. It's from the image. The RGB image is computed from the FITS data. You can think of the RGB image as a kind of summary of the FITS data, which may give us an hint that it can predict better if you just give it a summary of the data than the entire data set, but this still needs more analysis. And for the classification models with a single input output, we see again that to classify the galaxy, the model that performed best was the one that had the spectrum as input, which again, it makes sense because we look at the features of the spectrum to come up with this analysis of the galaxies. What was also interesting was the performance for the models that were trying to compute the galaxy zoo classification, which we see that 51% was the best result, but we don't feel this is a good result for a model classifying images that we are used to see today. We see deep learning models doing image classification with very high performance levels of accuracy. So there's something maybe going on here, either the way the images were created or from the statistic analysis, from the answers to the survey that originated the classification. So this also needs more analysis. What was also very interesting to see was the models that were given multi-input performed also very well. And for example, we can see that the model that was given all the inputs to classify the stellar mass actually outperformed all the individual models. So this gives us an hint that there are some combination here of the inputs of the data that are actually giving us more valuable information to inform this variable. And we see that the model that outputs the redshift at the S and the stellar mass at the same time achieved a very similar level of performance. So that intuition that there's some fundamental mapping that is common to those things, it seems to be true, because some part of this modeling to predict these two things, it's common.
Indeed, it's super interesting to see this multi-input output results. I have one question and then one from the chat as well. My first question is, this multi-input output model, for this one, you didn't run this hyperparameter brute force optimization, right?
Correct.
Okay, so it could have been even a little better.
Correct. For this model, I mean, all these things take time, and we didn't have time to do the exploration for these ones, for the hyperparameters. So what we did was try to go with a rule of thumb. What worked well for the others, let's use it here.
Ah, okay. So you leverage from the knowledge of individual inputs, single inputs, single outputs that you learn.
Yes.
To that. Okay, yeah, that makes a lot of sense. We have Nuno, who has a question, another Nuno, asking if the result will be in research work to be published, if it's already published, and if there is a possibility to access the data code used, or the repository of the code, if it's open source.
That is a perfect question in my world, because I have a slide later on that will answer that question.
Oh, amazing.
So if you can, thank you for your question, Nuno, but if you can just wait a couple of slides, I think we'll answer to that.
Great audience retention. Thanks.
So, the multi-input, multi-output models also worked well. I mean, we still have the problem for the Galaxy zoo classification, but we see for the subclass, he achieved a very good level of performance. And what was more interesting to me was to look at the model that takes all the inputs and comes up with all the outputs. Because we see, for example, for all the variables of interest, like the redshift, stellar mass, subclass, it achieved very good results when compared to the other ones. Of course, we still have that problem with the subclass, but the other three outputs are very in line with the best results we had for the other models. So that intuition that there's a common mapping, the network is captured this common mapping between these things. And this of course, this needs a more detailed analysis, but this is a very promising result. So that was part 2, models. Then we enter part 3, which are pipelines. And this is more in line with the discussion that we were having at the beginning, because we want these things to be applied quickly and applied easily. Because if you are analyzing data in real time that comes from your spacecraft to the ground, or even if you are analyzing data in real time in your spacecraft, you need to organize these things in the more systematic way that you can apply it better. And we did this by trying to come up with these pipelines, where the difference in our definition of pipeline is that instead of dealing with inputs and outputs, we are one level above. One pipeline is something that gets an object identifier as input, because we need the data for the object, and comes out with a result. And basically, to implement these pipelines, we use this MapReduce approach. If you are not familiar with this MapReduce approach, it's basically a way that you have when you want to process data that it's in a list or an array or any isomorphic data structure. You can use this approach to quickly process this data, in the sense that you can divide that array and have a function that applies to each part of the array. That's the map part. And then with all the results of those individual applications, you reduce that to a final result. And we use the same approach here, where once we get the object identifier, we get all the data that we need, and then a mapper model is responsible to calling all the models of interest, gives it all the models of the required inputs. Each model individually computes its output, and then we reduce all those results to a final output. And the way we reduce the results, it's very straightforward. If the output of the model is a real number, like for example, the redshift, the reduce operation does is a simple average. And in case of the classification outputs, what the reducer do is the most voted class is the one that is selected. And here we have the definition of some simple pipelines that we have created. And basically what you need to do to create a pipeline is just define the models that you want to use. And since we defined very well at the beginning our inputs and how the models are working, all this just integrates together very well. So for example, in our one-to-one model, what we do is we apply all the single input, single output models for all the outputs of interest. And then we take the mean of the result of all the redshift, the models that output redshift, and that's our final redshift. And we do this for every variable of interest. And of course, here our pipelines are only using the models that we created, but you can use this same approach to combine this with the results that come out of other tools. Especially, it will be more interesting to have other tools contributing to the final result that are not deep learning models. This way, you could combine together the ability for different fields of research to be used together to come up with a final result. And this, in a gist, is the idea behind the pipelines. But we took it an even step further because we created an API for these pipelines. So you don't even have to install all this code and all these models. You can just use the RESTful API. We selected the RESTful API because we don't need state here. You simply call, I have one API running on a virtual machine that you can try it out if you want. You can just call the URL that, and the URL, you put the pipeline that you want to process and the object identifier, and you just get as output this response in JSON, which is a very machine readable friendly format. And you can see here, for example, in these two examples, that the outputs are the outputs of combining the models together. And this API is interesting because you can apply the result of the combination of the models without installing and having to deal with all the details. But okay, since we have an API, why don't build an application on top of it? Because these things are integrating so well together that creating this application, this web application, was really easy once we had the API. And I can illustrate later if people are interested a little bit more, but basically the web application, here's a screenshot. You just select which model or pipeline you want to apply. You give the object identifier, and it will come out with the results. So this was my presentation for the work that was done. I also included these final remarks kind of slides because I wanted to mainly discuss two things very quickly. The first one is the threats to validity. This is an exercise that I think we, as practitioners of AI, should always be doing. We should be the more critics to our work. We need to discuss why didn't the results was as expected, or what can we do better. And of course, in this case, as we already discussed, there's this architecture that may be not ideal. There's this selection of hyperparameters that we can do better, or maybe we didn't train the models for enough time. We can also use some more detailed analysis of the data in our data set to try to see if there's some bias there or on the selected objects. And of course, for creating the data set, we also made some decisions. For example, the size of the image. Does that have an impact? Because by cutting the image in a smaller square, we may be cutting features of interest, or the other way around. You may be using an image that it's too big and the network is not looking at the points that you want with enough interest. And again, for our models, we didn't use any physics constraints. So in practice, we are building mappings that may not be compatible with our current knowledge of physics. This can be a bad thing and a good thing, because I mean, you can be discovering new things or new relations just because of this. But at the same time, you're not also taking advantage of this huge body of knowledge that we have in physics. Another thing that I'd like to do after the work is more or less done, besides the threats to validity, is also discuss what went good. What were the good lessons or the good practice that we did during this work, and then that we can apply in future work. And I compiled here a list of things that, in my opinion, were very relevant to this work. The first one is that we also always try to keep this open source mindset, because we want to be able to share all this code, all this data. We want other people to be able to reproduce everything. And we also want other people to be able to integrate these tools with their own tools or their own workflows. And I'm sure every one of us was already in the position that you say, like, to a friend or a colleague of work at work, I wrote a script to do that. And your friend tells you, oh, can you share the script? And you will tell something, oh, I can share it, but first I need to adjust it or do it properly because I did some things my way. But in general, what I'm trying to say is that when we are doing work that it's going to be shared with others, usually we come up doing a better work, more quality work overall. And this was our mindset, or at least the mindset that we're trying to go throughout all this work. And of course, another good practice is to discuss the threats to validity, what didn't work so well. Another thing that was very interesting for this work is that we kept this kind of formal specification for our data and our models. And I have a snippet here of this specification using a kind of Haskell programming language, if you are familiar with it. But the bottom line here is that we wanted to be able to discuss things without going to the implementation detail. So when we discuss, so what's the fits data type? Well, the fits data type, it's an n-dimensional array where the first dimension is the height, the second dimension is the width, and the third dimension is the bands. And that for most of the discussion, this kind of information is enough. And for example, we define the redshift as a real number, as a float. Then we can say that, for example, our model, our function that represents our model that computes the redshift from the fits, it's simply a function that goes from fits to redshift. And given the fits and redshift definition, we already know what this function has to do, the inputs that we'll get and the outputs that we'll get. And we can see that, for example, the pipelines we can define in a single line. So a pipeline is basically something that gets a list of models and an object ID, starts by getting the data for that object. The mapping function applies each model is a function, so it gets the data that it needs, and then you do a reduce on these outputs. And again, this is a way of being able to discuss things without going into the implementation details. And this one, I think, was very useful during this work. And this is probably why we had time to implement all these pipelines, all these APIs, and all these applications, one thing's on top of the others, because everything was very well defined and everything integrated very well. My last point on good practice about this work is about machine learning operations. Machine learning operations today is an active area of research where people are trying to come up with interesting tools and approach to use models in real-day life. And there's a lot of things going on about ML ops, but in this case, we did a lot of training models. We went through 100 plus training steps. It would be a mess to try to have this in notebooks or something like that. So what we did, we started with this ML flow tool, which is an open source tool. And we used it to define our model, our interaction with our models. So for example, when we wanted to try the image to redshift model with a different number of epochs, we will just run this command. And this makes everything very easy. And it will also track all the results for you. So in the end, you have this database with all the results for other models, and you have the history for the models and the inputs, and you can see the plots. And Probably at this kind of research, we don't need to use MLOps tools and approaches, but still using some specific features of some specific tools, we can take advantage of that. So that's just my opinion. And going back to Nuno's question about the open sourcing, all the things that I've been discussing are available from GitHub in a permissive open source license, and the data set is available from Zenodo. So you can just go to, I will share the links. You can just go to this link and download the data set if you are interested. There's more information about it. And in this, we also have this framework implemented in Python for the pipelines. And we have a different package repository for the models. If you want just to use the models and don't want to use the pipelines. And again, all these are on GitHub available and with a permissive MIT license. So you can just use it on your own research. And finally, we also have the code for the application online in a GitHub repository. And all the codes that, all the things that I discussed, it's available there. I hope this answers your Nuno's question.
Yeah, I think that's super great. We have a repository for the code, for the models, and also for the data. What a data scientist dream. That's great. And maybe also on the research side, have you been publishing in a in some research paper or a conference paper this work?
Not yet. I only finished this in last December, so we didn't have time yet to go through those considerations. But hopefully we can get some place to publish this.
I see. Yeah. Also, these things takes quite some time with the preparation, compliance to the journals. Often, for people who don't really know, when you want to publish a journal, you also have to comply with a journal author guidelines. So you have to respect a specific format and so on. Also for the reference and so it's not so straightforward. And then you have the back and forth with the reviewers.
Yes, agree.
But it's a great thing to do at least once in a life when you're in your studies. I think it's good. Oh, okay, I'll let you conclude.
Yes, I agree. Yeah. I only have a couple of more slides. So to conclude, during this work, we designed a total of 31 deep learning models. These were composed by 518 layers. And in total, this had more than 70 million parameters, all these models. And everything was trained, validated, and testing, and all if you look at the repository for the model, the MLflow database is there. So you can just look at the database to see the past training steps and everything. And of course, that's going back again to the advantage of using MLOps tool. So in the end, we got these pipelines that are able to infer some properties of interest for Galaxy. These pipelines are easy to evolve, and they can be systematically applied in different parts of space operations, and also for space design. For example, we have seen in the model that maybe sometimes we can go with, for example, only the selected bands of the spectra and not the entire spectra. And that will be enough for the things that we are trying to do. And this can provide relevant information for people that are designing missions. Because if you don't need so much information, maybe you can get it with a smaller instrument. If you have a smaller instrument or less data that you didn't need to downlink to your ground station. Maybe you can come up with a cheaper mission that is able to do the same goals, the same scientific goals. And again, all the data models available are available, public, under open source license. And my last comment to conclude is that this, as you have probably noticed, I used the sentence, this is very interesting, and this is very, there's a hint here, there's something going on. So usually we don't think on these models or pipelines as the end of the research. The models and the outputs of the models, they are just another tool in your toolbox. Probably your research needs more on top of this. So this takes me to my last slide, which is ideas for future work, where, of course, we have this section of ideas that are related more with the deep learning side of things, where, of course, you can build better models or come up with more data. But I think what's more interesting are these ideas for future work that are also related with the physics side of things. Because what will now be interesting is to do some kind of feature importance analysis to actually measure which inputs are more relevant for each output. And then get that intermediate representation that the models built and do a reverse engineering of that and try to relate with physical phenomena. You can, for example, our models build these intermediate representations. So you can try to relate those, for example, with the mass of the galaxy or the redshift. And then you can try to come up with a better idea of what were the features that the machine thought it were important. And this, for me, I think it's a very interesting thing to do. And again, of course, integrating this with physics informal models, this is on itself a discussion for another day. And I leave here also some references that are relevant for this presentation. And I will just like to end by acknowledge the contributions of Dr. Andrew Opfrin, Professor Catarina Lobo, and Professor Israel Matut from the Portuguese Institute of Astrophysics and Space Sciences, and their contribution to this work, and this quote from a famous statistician that's food for thought, that all models are wrong, but some are useful. And that's it for my presentation.
Really nice. Thank you very much, Nuno. It was amazing. Yeah, really a blast. I learned a lot. It was super clear. And people, if you have questions, it's also the time for you to ask a question to Nuno about, getting a job in space, or when you are in AI or anything like this. It's a great time. I really enjoyed your presentation. I mean, we could follow you from idea to an operational tool, all the way through some experimentation with pros and cons, and your decision, which taking decision during a project, saying, okay, we cannot do that because of time. It's really valuable, and also you emphasize on lessons learned, future work. I think it's like a masterclass for people who wants to to try to apply it to a project end to end. So yeah, I'm really happy to see this presentation. I learned a lot as well.
Thank you.
And yes, this is funny because this quote, all models are wrong, but some are useful. For quite some weeks, I added in the office, it was like my screen saving quotes on my screen. I really like it. It's good because it reminds us to stay humble.
Yes, and one corollary of this quote, I think, or at least for me, is that sometimes you need to take a step back. Sometimes we get too caught up in the models and getting 1% more of precision, and sometimes we should take a step back and look at our model is wrong, but what can I learn from it? What can I do? And take another look at the problem. And is this the correct approach or not?
Yeah, and you mentioned physics. How can we use physics? How can we help astrophysicists then using this potentially doing model diagnostics to analyze errors? Maybe with someone who is more an astrophysicist, and then discussing, okay, what do you think? Checking model features and so on. This could be instead useful. This is also a good lead-in because I'm not sure to which extent in 2 weeks, Simon, the next speaker, will talk about physics-informed machine learning. He may talk about such topic as well. But it's true that sometimes adding a bit of first principle, the physics we know, doesn't hurt, right?
Yes, of course. But what I've seen a lot is that if you are from the deep learning field of research and you go, for example, talk to someone that's doing research in fundamental physics or physics theory, you shouldn't start a conversation like, oh, I have this model with 99% accuracy. Because usually people are more interested in what's inside the box than the box itself. And you need to come up with a clever way to tell, and this is why this kind of relevance, importance, feature analysis is important, because you want to come up with to this person that is studying this and say, look, I have this model that it seems that it's showing that the mass of the galaxy, it's important to calculate feature X by this amount. And this is a much more interesting conversation to have.
Indeed. Yeah. Do you have, are you still working on this now, or because I know now you're so you say you're working at the European Space Operations Center. Are you still working on that, or are you working on another topic?
No, I'm currently working more on the mission operations side of things. So I'm not working right now in too much detail of the astrophysics side of things. But
Okay.
that was another reason that pushed us to have all these things available online and under an open source license. If there are more people interested, they can just continue the work. And if they just reach out to me, I can give everyone permissions on the repositories to do whatever people want.
Okay, that's good to hear. I'm sure if people will watch this, they will like yeah, some people want to try themselves or build a model. So have you done like the first baseline on this data set, or do you know if other people have also attempted something like you did?
There are plenty of studies about this, not about our specific data set, but about the SDSCS survey. But I mean, you need to have to, of course, I didn't go into that detail here, but you also need to take a look at what's also done on top of that survey, because there are some interesting things available already in the literature.
Okay, I see.
I also shared in the chat all the links that I used in the presentation. So all the links that are there if people want to check anything.
Very good, thanks. A lot of food for thought here. Okay, so I think it's slightly time to say thank you to Nuno for the great presentation. Some people already said their appreciation, that they really liked it. Do you have some final words, or maybe some reading recommendations, something you would like to say to the audience, if anything?
No, I just wanted to thank you again for the invite and for the very always interesting discussion. And I don't know, just go out and apply deep learning models to everything.
Great. Thank you very much, Nuno. Glad we could organize this since we first met last year at in Paris during the conference. And see you around probably in Germany when I come back. All right. So thank you everyone for joining. Thank you, Nuno, again. The replay will be made available in YouTube Rocket AI channel. Next event will be in April 4th, where we will be talking about space weather modeling with Simon Bourria, who has worked at NASA and now is doing a PhD in space weather modeling with AI. So this will be very much on the topic. So yeah, let's meet in 2 weeks. So thank you again, everyone.
Thank
Bye-bye.
you. Bye.